The largest galaxies in the universe are supermassive galaxies with trillions of stars. We can find them at the center of most major galaxy clusters, and they're called supermassive because they contain hundreds of trillions of stars. That's 1,000,000 times the size of our galaxy. But how did these gigantic galaxies form so quickly? It might sound obvious to say that these massive galaxies formed gradually over billions of years. But it turns out that that's not what scientists think anymore. They have evidence that suggests that most supermassive galaxies formed really fast, in just a few 100 million years after the Big Bang. And the reason for this has to do with a process called supernova feedback. Stars live fast and die young. Stars form from giant clouds of gas and plasma that collapse under their own gravity. The material is heated to millions of degrees in the process, which makes elements like helium and lithium that can then fuse to make even heavier elements and eventually iron. When a star fuses iron, its core collapses and blows apart in a supernova explosion. This blasts heavy elements out into space, and then those elements can become part of new stars and planets. So stars constantly recycle the material they're made of. And while this process is going on, stars also emit light and heat in all directions. It would be great if there was a nice balance between the inward pull of gravity and the outward push of stellar energy, and everything would stay nice and stable. But sometimes one force wins over the other. In galaxies today, most of them have an elegant balance between the two forces, but some of them don't. They're losing gas from their outer regions, and that means they won't form many new stars in the future. And we know that something caused this imbalance, but we aren't sure what. This is known as the feedback problem. We know that star formation in galaxies depends on how much gas they have. If there isn't enough gas, there aren't enough raw materials to make new stars. But why do some galaxies have so much gas and others have almost none? One leading hypothesis is that supernova explosions are so powerful that they blow away all the gas in their host galaxies. That seems to make sense, but astronomers haven't been able to get the numbers to add up until now. A team of researchers used a computer simulation to model how supernova explosions affect the gas in their host galaxies. Their simulation included around 10 million stars and accurately recreated the life cycle of a star, from its birth in a giant cloud of gas to its death in a supernova explosion. Then they looked at several factors, including how the strength of the supernova explosions changed over time, how far away each explosion was from the galactic center, and how much mass each star had. Their simulations suggest that supernova from low-mass stars can blow gas out of galaxies, but it is mostly the supernova from high-mass stars that have the power to clear a galaxy of gas. And it turns out that the key factor in determining whether or not a galaxy loses all of its gas is the average metallicity of the stars. Metallicity is just a fancy way of saying what percentage of the star is made of elements heavier than hydrogen and helium. When stars explode, they release metals back into the galaxy. And the more metals a star releases, the more massive it is. So if a galaxy has a lot of massive stars, they'll release a lot of metals. And if there's enough metals in a galaxy, the next generation of stars will form with lots of metals. And when those stars explode, they won't have the same effect as the first generation of low metallicity stars. They'll be less efficient at blowing gas out of the galaxy. Basically, you could say that the galaxy builds up an immunity to being blown apart. In the early universe, the average metallicity was very low, so supernova were very effective at stripping away the gas in galaxies. But as the universe evolved and stars exploded and recycled their material, metallicity increased and galaxies became immune to being blown apart. So the early universe must have been a pretty violent place. The researchers showed that in simulations where the metallicity was low, galaxies lost a lot of their gas very quickly. After just a few 100 million years, they had only about 1/10 of their original amount of gas. Since galaxies form new stars from their gas, That means they couldn't keep forming stars at the same rate as before. Now, in modern times, galaxies have more metals, so supernova don't blow away as much gas. This means that galaxies can continue to form stars at a steady pace for most of cosmic history. But the researchers also found that sometimes the gas in galaxies gets hot enough that it just blasts out of the galaxy altogether. This is known as a galactic wind, and it's thought to be driven by the collective energy of supernova explosions. They confirmed that most of the gas stripped from galaxies in their simulations was expelled in these gigantic galactic winds. The researchers think that these winds may have played a role in the formation of the gigantic supermassive galaxies we see today. When galaxies collide, the gas in both of them heats up and forms a gigantic cloud around the center of the two galaxies. Over time, this gas cools down and forms a disk of stars. This process can repeat multiple times, and each time it does, the disk of new stars forms closer and closer to the center of the growing supermassive galaxy. Eventually, the central region of the galaxy is so dense that the supernova explosions can no longer blow gas out of the galaxy. At that point, the galaxy becomes immune to supernova feedback and can continue to grow gaining trillions of stars in just a few billion years. But this doesn't explain why some galaxies have a lot of gas and others don't. It turns out that the answer depends on how close the galaxies are to each other. The researchers found that when galaxies are relatively far apart, the gas they expel cancels each other out and they end up with just a regular old galaxy. But when galaxies are close enough together, the gas in one galaxy can escape the gravitational pull of the other, and it ends up just getting pulled right in. Once inside the other galaxy, this extra gas actually boosts the star formation rate. So you get more supernova, and more supernova means more metals. So the second galaxy becomes immune to supernova feedback and can start accreting more and more galaxies until it forms a gigantic structure made up of smaller galaxies. This is basically the opposite of what scientists thought was happening. Initially, they thought that more supernova meant more gas got blown away, and fewer supernova meant more gas remained. But this research shows that it's actually the other way around. More supernova lead to more gas being gathered together, and fewer supernova lead to more gas being blown away. The researchers say that their simulations are the first to capture this positive feedback loop between metals, star formation, and gas accretion, and it explains a lot of things that astronomers have observed. For example, the biggest galaxies have the lowest amounts of gas. The smallest galaxies have the highest amounts of gas. The rate at which galaxies consume their gas supply depends on how big they are, and even the distribution of metals around the centers of galaxies. What's more, the team thinks that these simulations can help them figure out what the early universe would have looked like. If they run the simulations backwards, they can see what the galaxy formation process might have looked like before metals were recycled into stars. They found that low metallicity galaxies were more likely to completely blow themselves apart than galaxies with higher metal. And in the early universe, most galaxies were low. So astronomers are hopeful that this research will help them understand what happened to all of the missing galaxies. According to the standard model of cosmology, the universe should have roughly the same number of small and big galaxies, but observations show that there are far more small galaxies than big ones. So somewhere along the line, most of the medium-sized galaxies seem to have disappeared. And one idea is that they all got blown apart by the supernova explosions in their host galaxy clusters. Now astronomers have a better idea of how that might have happened. I find it amazing that we can study such distant objects that existed so long ago. Every time we learn more about the early universe, it seems like it was a more violent place than we expected. I guess it makes us lucky to be alive at a time when the universe is nice and stable. And it's amazing that we can learn so much about the universe with mathematics. The work done by the team in this paper is a great example of the power of mathematical modeling. If you want to learn more about how models work, you can take Brilliant's course on mathematical modeling. In this course, you'll learn how to use math to build models that describe real-world phenomena. You'll explore some famous examples like the Lotka-Volterra equations, which are used to model predator-prey interactions. These simple equations can accurately predict the population dynamics of species, like how the lynx and hare populations in Canada are linked. Thanks for watching and learning with us!